Okay, let's unpack this. Today, we are diving into one of the, I think, most pressing architectural challenges of the modern enterprise, and that is trusting the machines that, well, that run the business. We're moving past the era of passive instruction following AI and really straight into the world of truly autonomous, goal-directed agents.
That is the defining line in the sand, isn't it? I mean, traditional automation, the systems we've built and audited for decades, they were fundamentally deterministic. They followed a rigid flow chart. If X happens, then execute Y. But the sources we've examined, and particularly this deep architectural handbook focusing on agentic AI trust, they describe systems that perceive their environment, they reason about complex objectives, generate their own multi-step plans, and then, and this is the key part, they execute those plans with minimal human intervention.
And the mission of this deep dive is, well, it's absolutely crucial. How do we establish foundational, verifiable trust in a system that literally reasons for itself? The systems we're talking about aren't just summarizing text anymore. They're actively managing supply chains, executing financial trades, or making resource allocation decisions that can affect millions of people. So we need the technical framework that makes every single one of those autonomous decisions traceable, auditable, and at the end of the day, accountable.
The stakes are incredibly high,
Yeah.
especially in regulated or high-stakes sectors. Just consider an agent deployed in a financial services environment that's making decisions about granting or denying critical services. Or an agent in logistics rerouting global shipping based on dynamic weather patterns. If that decision fails, or if it violates regulatory guidelines and an auditor or a regulator comes knocking and asks, why did the system do that? Well, the organization needs more than a shrug.
Right. The model decided is not an answer.
It's not an answer. The technical framework has to provide the cryptographic, verifiable evidence, the complete lineage, the precise reasoning path. If you can't prove why a decision was made, you are absorbing massive legal and reputational exposure. That proof is what a well-designed trust architecture delivers.
So let's start by defining the core problem facing, I think, every architect today, which is the interpretability gap. Why are these new agentic systems so inherently opaque? Unlike the systems we're used to, where you could literally just print out the decision tree.
It all comes down to the shift in their fundamental logic basis. Think of traditional automation like a mechanical Swiss watch. The gears are static, the logic is predictable. If you input A, you always get B. Agentic systems, however, are powered by these large-scale reasoning engines and semantic resolution systems.
Which moves us from that mechanical logic to something far more fluid.
Precisely. Their logic is fundamentally probabilistic. The agent is receiving a high-level objective, maybe in natural language, and it converts that objective into a complex, high-dimensional mathematical embedding, a vector representation of the goal. It then uses contextual inference and similarity scoring to find the most relevant tools or functions or knowledge to solve that goal. And because it relies on inference and probability, not hard-coded rules, the execution path is dynamic. It's context-dependent.
So you're saying identical inputs can produce divergent outputs?
Absolutely. The agent might consult an internal memory store that has changed since the last run, or the external environment state, a fluctuating stock price, a sudden weather alert that might subtly influence the probabilistic path it takes.
Just adaptive.
The system is adaptive, but that adaptation comes at the cost of the old deterministic guarantee. It completely moves the audit focus. We're no longer verifying pre-written rules. We're continuously assuring autonomous intent as it unfolds in real time.
And that makes the need for explainability, while it makes it non-negotiable. It becomes the primary mechanism for establishing what the sources call justified confidence in mission-critical operations.
It is the bedrock.
Yeah.
And the sources highlight two enormous risks if we fail to implement robust explainability. The first, as we mentioned, is that legal and reputational exposure. If a system denies a critical service, say an automatic insurance claim, and you can only tell the customer the model decided it, that's a systemic failure.
You're in big trouble.
You are. You have to be able to present the full evidentiary package. The raw inputs, the policy violations it detected, the specific policy rules that were triggered, and the agent's reasoning that led to that denial.
And the second risk relates to engineering resilience, which the sources term explanatory debugging.
Yes, and this is critical for maintaining the system after deployment. If a major failure occurs, let's say the agent executes a flawed plan that deletes customer data, engineers have to be able to instantly find the root cause. Did the agent experience a tool call error? Did it misinterpret a key piece of documentation? Or maybe the most insidious possibility, did it develop a latent bias after interacting with unexpected data, leading it down an unintended path? Without a clear, traceable reasoning path, debugging becomes impossible. You're just staring into an opaque box.
And this opacity problem, it's magnified exponentially when autonomous agents start working together, right? If you have an entire team of specialized agents, all coordinating to achieve a large objective, you get into what the sources call provenance obscurity.
This is a major accountability failure. Imagine a supervisory agent receives an objective, maximize quarterly profit. It delegates a subtask, find the optimal supplier for widget X to a subordinate procurement agent. That subordinate agent takes the action. Now, if that action leads to a compliance violation or a catastrophic supply failure, who is accountable?
So in plain language, if the delegation chain isn't perfectly recorded, you can't tell which machine to fire when the error hits the news?
Precisely. That handover, that delegation, it must be explicitly justified, recorded, and tied back to the initial supervisory intent. If the subordinate agent wasn't properly authorized or if the supervisor gave ambiguous instructions, the lineage is lost.
Yeah.
And provenance obscurity renders the entire decision chain unauditable and, frankly, destroys any hope of attributing responsibility.
Here's where it gets really interesting. Let's look at the core differences laid out in the architecture handbook. If section 1 was about defining the why of opacity, this contrast is really the blueprint for the shift in architectural focus.
The old system properties were all based on stability. The logic basis was static rules and hard-coded trees. Now it's probabilistic reasoning and semantic resolution.
A huge shift.
A massive one. The execution path used to be purely deterministic. Now it is dynamic, context-dependent, and adaptive.
And crucially, the audit focus has completely changed. We were comfortable with simple input-output logging and code review, the external-facing artifacts. Now we have to demand insight into the internal state. Reasoning traces, intent logs, and state deltas. These subtle, ephemeral cognitive movements within the agent that led to the final output.
Which means the trust model itself shifts entirely. It moves from a passive verification of pre-written rules to demanding continuous assurance of autonomous intent. And that's a proactive, real-time necessity that has to be built into the infrastructure. It requires structural controls to govern intelligence.
So we need to architect a proactive trust model. The handbook lays out the foundation for this by defining 4 core principles that have to be integrated throughout the entire system lifecycle: accountability, transparency, integrity, and resilience. Let's walk through these pillars as really architectural constraints.
These 4 principles must guide every design choice, every deployment decision. Let's start with accountability, focusing on what they call identity-centered governance. The principle is simple. Every single action must be definitively attributed to a responsible entity, whether that's a human operator or a specific named digital agent.
How do you achieve that level of rigorous identity management, though? Especially since agents can be ephemeral. They might pop up to handle a surge of tasks, complete them, and then just disappear.
You achieve it by managing the identity lifecycle rigorously, using what are called task-scoped, time-bound credentials. So instead of giving an agent a single persistent service account that lasts for months, you provision a specific token with the bare minimum privileges required for the task.
And that token expires quickly.
Exactly, it expires rapidly. This prevents the identity lifecycle gap, where these temporary or poorly tracked agents can act without a verifiable record. Every decision, every API call has to be linked to a unique, non-repudiable agent identity through the audit trail. This is essential for forensics, especially to prevent things like replay attacks where a bad actor tries to reuse a token from a successful past action.
That distinction, task-scoped identity, is so key. If you can't attribute the action, you can't hold the entity responsible, whether that entity is a piece of code or the team that launched it. Okay, moving on to transparency. This is where we get the insight into the why.
Transparency requires capturing the agent's full internal cognitive state, not just the final outcome. We have to capture the entire sequence: intent, plan, execution, action. The intent is the goal it received. The plan is the step-by-step procedure the agent formulated. And the action is the resulting execution command. Capturing this entire sequence allows for the full, granular reconstruction of the reasoning path, satisfying both stakeholder curiosity and deep regulatory inquiries.
And you mentioned a critical element here that separates basic logging from true transparency. It's about justifying the actions the agent didn't take.
The why not scenarios, yes. This is vital for compliance and for alignment. Transparency is only complete if the system can explain why alternative, permissible actions were rejected.
So, for example,
If a credit scoring agent approves a medium-risk application, The justification must also include why it rejected the slightly lower risk application that failed to meet a certain policy threshold. This transparency provides massive context. It reveals the policy boundary and ensures the human auditor's mental model aligns perfectly with the agent's operational policy.
Okay, pillar 3, integrity. We often associate integrity with data security, but here it sounds more like ensuring the agent's internal reality hasn't been corrupted.
That's a perfect way to put it. Integrity is all about ensuring the system remains uncorrupted throughout its lifecycle. And this defense starts at the perception layer. The agent's world model, its internal structured representation of external reality, is built entirely on incoming data.
So if that data is poisoned,
If that data is poisoned, corrupted, or unauthenticated, the entire decision-making process is fundamentally flawed. Therefore, integrity requires strict authentication at the perception layer to validate the provenance of all incoming data. You need cryptographic proof of where the data came from, and that it hasn't been tampered with before the agent even begins to reason over it.
and finally, resilience. This is the architectural admission that systems are not perfect, so we must design for graceful, contained failure.
Absolutely. Resilience is all about setting robust safety boundaries. The sources call for implementing constrained autonomy zones. Think of these as safety fences, predefined limits within which the agent is authorized to operate. If an agent manages to plan an action that approaches or crosses one of these safety boundaries, say, exceeding a defined spending limit or trying to access a segregated data store execution, has to pause.
And what happens during that pause? What's the mechanism?
The action is subject to mandatory validation checkpoints. These checkpoints can range from something automated, like a policy-based verification by the policy enforcement engine, to a human-in-the-loop oversight mechanism. The goal is to ensure that a local planning error or a minor cognitive exploit doesn't propagate into a systemic catastrophe. The architecture must always assume the agent might try to fail or go rogue and build the infrastructure to contain that risk.
These 4 pillars are great guiding principles, but to make them real, we need a concrete structure. The sources outline a robust, multi-tiered reference architecture for governed agentic systems. This is where the technical stack ensures autonomy is structurally controlled. It's kind of like building a nuclear submarine, right? You can't trust the captain unless you trust the hull and the engine.
That analogy is spot on. This framework separates concerns, ensuring each layer has a distinct function and, critically, a specific governance responsibility. You cannot trust the agent unless you trust the foundational infrastructure it operates on.
Let's start at the very base, the hull. Layer 1, the perception and world modeling layer.
This is the critical interface where the agent takes in all its external stimuli. Sensor data, API streams, user prompts, database queries, everything. And if you consider that data provenance is the key trust mechanism here, this layer's job is to normalize those diverse inputs into structured observations and then validate their source.
So it's the gatekeeper for reality.
It is. If the agent's internal world model is built on compromised or unauthenticated data, the entire reasoning process, all subsequent layers, is invalid. This layer is the primary defense against data poisoning attacks.
Okay, moving up to the engine room. Layer 2, the cognition and reasoning layer. This is where the actual intelligence resides.
Correct. This is the central reasoning engine. It receives a structured objective from layer 1 and uses complex methodologies, chain of thought, symbolic logic, or large language models to decompose that abstract goal into a series of actionable subtasks. The auditability requirement here is paramount. This layer must generate detailed reasoning traces concurrently with the planning process.
So not after the fact.
Never after the fact. These traces are the agent's verifiable internal monologue, documenting its deliberation, its rule evaluations, and its knowledge retrieval steps. An auditor should be able to look at this trace and understand how the agent weighed competing constraints.
Then we hit layer 3, the memory and continuity module. This seems like the most sensitive layer from a compliance perspective.
It absolutely is, especially concerning things like data privacy and residency rules. The memory module provides temporal context. You've got short-term memory, which maintains the context of the immediate session, and then long-term memory, which stores generalized episodic knowledge and learned patterns. The governance criticality here is immense. Memory must adhere strictly to regional data residency directives. If the agent is operating in Europe, its memory cannot persist sensitive data on U.S. servers.
Of course.
And furthermore, the architecture has to prevent sensitive information from being leaked across distinct agent sessions or persisted indefinitely without explicit authorization. It requires the same rigorous governance protocols as any highly regulated database system.
Okay, layer 4 is the action layer, the actuation and execution layer. This is where the plans from layer 2 are translated into, well, physical or digital impact.
This layer is the system's hand on the controls. It calls tools, executes APIs, sends commands to external systems. Trust is enforced here by the principle of least privilege and secure, authenticated gateways. An agent should never be able to execute an action directly on a high-privileged server. It has to interact only through dedicated secure APIs. And every single execution event must be logged with comprehensive metadata: the identity of the initiating agent, the specific rationale drawn from the reasoning layer, and a verification of the observed external outcome.
And finally, layer 5, the air traffic control, the governance and audit substrate. This holds the separation of concerns.
Yes, this layer monitors and regulates the interaction between all the others. Its core function is the decision intelligence layer, which enforces that separation between reasoning in layer 2 and action in layer 4.
It's a mandatory checkpoint.
An absolutely mandatory, independent checkpoint. The critical components are the mandatory interceptors, which we'll detail in a moment, that act as sidecar proxies to prevent any execution bypass.
But let me challenge you on this critical point. The policy enforcement engine, the PEE, lives here in layer 5, and it evaluates every request against contextual policy before execution. If the PEE intercepts every API call in, say, a high-frequency trading or complex logistics environment, doesn't that introduce significant, potentially paralyzing latency? How do architects balance security checks against performance?
That is the $64,000 question in autonomous architecture, and the balance is addressed through several mechanisms. First, the PE operates on optimized declarative policy sets, not complex, slow models. Policies are precompiled and are basically highly efficient Boolean logic checks.
So they're fast.
Very fast. Second, the PEE uses contextual metadata, which is attached by the interceptor. This allows it to bypass deep processing if the request falls within safe, pre-approved, constrained autonomy zones. And third, and maybe most importantly, in extremely high-frequency scenarios, a calculated latency trade-off is often necessary. The architectural philosophy mandates that governance cannot be sacrificed for speed. If performance is absolutely critical, architects may have to reduce the agent's autonomy and rely on pre-validated execution paths, accepting lower efficiency for verifiable compliance. The PEE remains the non-negotiable gatekeeper.
Okay, let's drill down into the mechanics of accountability, starting with intent resolution. We noted the shift from static routing to semantic routing earlier. When the agent is making a statistical guess about which tool to use, how do we trust that probabilistic match?
This is where we see the transition from predictable engineering to really governing an intelligent system. In the past, if a user typed generate report X, the system statically routed to the report X function. With semantic resolution, the agent takes that natural language input, converts it into that high-dimensional vector, and then searches its tool registry for the closest mathematical similarity.
Which means the intent is a purely statistical recommendation. And that sounds vulnerable to ambiguity, or worse, an attacker crafting an input that semantically matches a high-privilege function, even if the user didn't explicitly request it.
Precisely. That purely probabilistic match must be immediately wrapped in control logic. The resolved intent, which is still just a recommendation, has to be passed to layer 5. There, the policy enforcement engine evaluates it against explicit enterprise policies. So, for example, if the semantic match suggests accessing the payroll database, the PEE checks the initiating agent's credentials and the context of the request.
And for auditability?
For auditability, the system has to log the semantic match parameters, the confidence threshold, the distance metric used, so we can confirm the agent wasn't operating on a weak, speculative match.
Next, cognitive orchestration. We mentioned the continuous loop of thinking and acting, the reason plus act pattern. This dynamic nature sounds incredibly difficult to audit.
It requires continuous capture. The agent operates in this perpetual loop. It generates a reasoning trace, it executes a small plan fragment, it observes the outcome through layer 1, and then it updates its strategy based on that new data. To maintain auditability, every single iteration of this loop must be captured and logged.
Why is capturing every iteration so crucial? What does that prevent?
Well, first, it ensures the system adheres to operational constraints, allowing us to review exactly why the agent modified its approach mid-plan. Second, and critically, it prevents one of the unique failure modes we discussed, the infinite reasoning loop. If an agent is constantly caught planning, reflecting, or making non-productive tool calls without resolution, it wastes massive resources and can paralyze the system. By enforcing iteration limits and time-based circuit breakers and logging every step, we ensure the process terminates either successfully or safely.
Okay, now let's move to the architectural cornerstone of accountability: action provenance and mandatory interception, the non-negotiable zero bypass approach. This is about guaranteeing the agent can't just go rogue.
This is the foundation of trust. The core problem is that an autonomous agent, especially a powerful one, might try to communicate out of band, completely bypassing the centralized logging or governance layer.
And if it does that,
If an agent can execute a command like calling an external API without passing through a checkpoint, the audit trail is instantly compromised and your policy enforcement is useless.
so the solution is the mandatory transparent interceptor pattern, essentially a required sidecar proxy. How does the zero bypass guarantee function technically?
Architecturally, it's a strict network requirement. The network topology must be microsegmented such that the agent component physically cannot communicate with the external world or other network segments unless its traffic is routed through its designated sidecar proxy.
It's a literal enforced gateway.
It is. The interceptor is then tasked with 4 critical functions that ensure non-repudiable provenance and integrity.
Okay, function one, metadata enrichment.
The interceptor captures the communication packet, the tool call, or the API request, and it standardizes it. It enriches the packet with comprehensive audit metadata, the unique agent identity, the precise data origin, the temporal context, and a reference back to the original Layer 2 reasoning trace. This creates a foundational audit record.
Function two, parent hashing. This is where the cryptographic chain of lineage is established.
This is a brilliant mechanism that ensures the integrity of the sequence. Every standardized packet has to include a cryptographic hash of the previous reasoning step or action. So we can describe it as, h sub n equals the hash of packet n combined with h sub n minus 1.
That sounds dense. Let's use the analogy you suggested earlier.
Think of it like a digital paper trail for your actions, but one where the receipt for today's action cryptographically includes a verifiable sliver of yesterday's receipt. It creates an unbroken chain. If an external actor tries to slip a forged action or reasoning step into the middle of the chain,
The hash won't match.
the hash won't match the subsequent action, and the entire chain is instantly invalidated. You have verifiable, tamper-proof lineage.
Function three, cryptographic attestation.
After enrichment and hashing, the interceptor uses a private key tied to the agent's unique identity to sign the entire packet. This digital signature ensures non-repudiation. Once it's signed, no party, not the agent, not the platform, can later deny that this specific action was initiated by that specific attributed identity at that precise moment.
And function four, which ties the internal intent to the external result: state delta verification.
The interceptor records the entire response from the external system. This allows the governance substrate to verify the state delta, the difference between the external system state before and after the action. Did the agent intend to change a client record? The state delta verification confirms that the external system actually reported that the change was successfully committed. This critical step verifies the effect, not just the intent, making the trust architecture active and self-defending against discrepancies.
The technical audit trail is robust, but we still face the barrier between the machine's internal technical artifacts, the state vectors and attention weights, and the human auditor who needs a narrative. How do we bridge that human-machine gap to make the trace useful?
We have to move beyond just simple token logs. We need to leverage the agent's own reasoning ability to translate those latent technical states into human-readable narratives. The sources emphasize something called state delta encoding, SDE.
Explain SDE. Why is capturing the change in the hidden state necessary for an audit?
So when an agent is reasoning, say, evaluating several options to solve a complex problem, its internal hidden state vector, let's call it H, is constantly shifting as it processes new information, weighs different concepts, and calculates risk. SDE captures the sequence of these changes, the trajectory of deltas, in its hidden states during deliberation. It doesn't just record the final word, it records how the thought evolved over time.
So if the agent initially prioritizes speed, but then it reads a compliance document and its risk weighting suddenly increases, that shift is mathematically encoded.
Precisely. If h of an I is the state vector at step I, the difference, the delta, between that and the previous step, h sub I minus 1, reveals the precise logic shift that occurred behind the surface language. This is how auditors find the inflection point in the decision-making process, the exact moment the agent prioritized compliance over efficiency or risk over profit. By summarizing these encoded deltas, the system can generate a clear, intrinsic narrative that explains the priority changes.
And this feeds directly into the power of contrastive explanations, those why-not scenarios that build immense confidence.
Counterfactual explanations are mandatory for justified confidence. The agent must justify not only what it did, but why it rejected the next best alternatives. This is crucial for aligning human judgment with machine policy.
Can you give us a concrete example of how this looks to a human stakeholder?
Sure. Imagine an autonomous wealth management agent recommends allocating client funds to Portfolio A. A contrastive explanation would state something like, Portfolio A was selected because it satisfied the maximum regulatory risk threshold of 3%. Portfolio B, which offered a slightly higher projected return, was rejected because its expected regulatory risk was 3.1%, violating the declared constraint.
So it identifies the exact reason.
It identifies the minimal change in constraints, that 0.1% difference in risk, that would have yielded a different outcome. This allows the human to verify instantly whether the agent's operational policy perfectly matches the fiduciary goal.
All of this relies on the audit artifacts remaining perfect, hence the need for immutable audit trails moving beyond simple flat logs.
Traditional logs are easily modified, and that's a huge problem. Agentic systems require a ledger of truth. By using hash chains, where every signed interaction packet cryptographically links to its predecessor, you establish cryptographic integrity. If someone attempts to modify the historical record of a decision, the subsequent hashes will fail the verification check, providing instant, irrefutable evidence of tampering.
And it scales up.
For global, high-volume systems, the use of distributed consensus algorithms and structural tools like Merkle trees is necessary to maintain consistency across the entire enterprise.
And you made a point about the ledger being actuation-centric. Why is tracking the effect of the action, not just the intent, the ultimate form of integrity verification?
Because intent does not equal outcome. An agent might intend to process a transaction, but a network error, a database lock, or an external system failure might prevent the transaction from ever completing. If your ledger only records the agent's intent, you miss the failure.
Right, you have a mismatch with reality.
Exactly. The actuation-centric ledger forces the system to verify the expected external state delta. For instance, if the intent was to change invoice number 456 status to paid, the ledger must wait for verification from the external accounting system that the status actually changed. This prevents system drift, where the agent thinks one thing happened, but reality diverged from accumulating quietly and leading to silent, massive data corruption.
Okay, now for the critical risks. The unique failure conditions inherent only to autonomous goal-seeking systems. We need to detail the 4 critical modes that simply didn't exist in hard-coded software.
The first is goal misalignment. This is arguably the most dangerous non-malicious failure. It occurs when the agent's internal optimization objective deviates from the overarching intended business outcome.
Like the procurement agent we talked about, prioritizing cost savings so aggressively that it optimizes itself right into choosing suppliers that are financially unstable, despite the primary business goal being supply chain resilience.
Exactly. The agent is still behaving rationally according to its internal reward function, but that function is misaligned with the human stakeholder's highest values. Mitigation requires robust constitutional guardrails. These are meta-policies that sit above the agent's primary objective function, to constrain the agent's search space and ensure its optimization criteria are always tethered to the highest level of human-defined policy, like safety or stability.
The second is the infinite reasoning loop we touched on.
Right. This failure mode involves the agent getting stuck in an endless, unproductive cycle of planning, reflecting, or attempting to use a faulty tool. This is often triggered by ambiguous goals, conflicting policy constraints, or unexpected environmental obstacles it just cannot resolve. The risk is resource exhaustion and operational paralysis.
Then the fix?
The fix is architectural. Mandatory iteration limits and time-based circuit breakers installed at the orchestration layer to forcibly terminate any process that fails to resolve within a defined period.
Third, and the most frightening from a security perspective, cognitive exploits or logic hijacking.
This is a profound vulnerability that undermines traditional security. It happens when malicious inputs, like a clever prompt injection, trick the agent into overriding its security protocols, its system instructions, or its constitutional guardrails.
So wait, the attacker isn't breaking code, they're subverting the reasoning process itself.
Precisely. They are hijacking the agent's logic. An attacker can use natural language to convince a highly privileged financial agent to literally ignore all the millions of dollars spent on its security architecture. Mitigation here requires rigorous input sanitization, but crucially, it relies heavily on those mandatory interceptors we discussed in Section 4. The interceptor has to evaluate the intent against the known good policy before the action is executed, ensuring the agent cannot execute a privileged command based on a poisoned input that violated its security mandate.
And finally, data exfiltration through overpermissioning.
This typically stems from poor identity governance. If an agent is granted a broad, long-lived tool permissions, for example, access to the customer database in the ledger system, an attacker who achieves a cognitive exploit can then trick the agent into using those tools to leak sensitive data out of band. The architectural defense is strict adherence to the principle of least privilege, using those task-scoped ephemeral tokens. If the agent's job is only to update the ledger, it should not have the ability to read the HR database. Simple as that.
We've built the architecture, we've defined the risks. Now, how do we measure if all this structural rigor is actually working? We need to move beyond simple speed and accuracy metrics and establish a balanced scorecard for trust and governance.
We need metrics that emphasize compliance and verifiable accountability over just raw performance. The first one is the explanation completeness score.
What does that measure practically for an auditor?
It measures the sufficiency of the explanation provided. So, does the reasoning trace, once translated into a narrative, contain enough information for a human auditor, or even supervisory evaluation agent, to reliably predict the primary agent's next action? If the explanation is complete, the reviewer should be able to recover the agent's true decision logic from the narrative alone. If the human remains confused, the completeness score is low, indicating a critical gap in transparency.
Closely related is explanation density. We don't want to bury the auditor in 50 pages of internal monologue.
Exactly. Density quantifies the informativeness relative to its length. We need high-quality, concise explanations. Low-density explanations are massive, rambling narratives full of noise that just increase the cognitive load on auditors. High density means every token contributes meaningfully to understanding, respecting the auditor's time while ensuring full compliance review.
We also need to track failures in the execution layer, which is the discrepancy rate.
The discrepancy rate is crucial for tracking systemic drift. It measures how often the agent's stated intent, its Layer 2 plan, differs from the actual system outcome. The Layer 4 observes state delta. A high discrepancy rate points to either severe flaws in the agent's internal world modeling, it thinks it's doing one thing but external reality dictates another, or a fundamental unreliability in its actuation layer. It flags an immediate architectural review.
And the most direct safety metric tracked by the governance substrate, the policy violation frequency.
This is a real-time safety indicator. It counts how often the agent's proposed plan was rejected by the policy enforcement engine before execution. If an agent is constantly proposing actions that the PE flags as exceeding constraints, perhaps trying to access an unauthorized API or initiating a trade outside a set risk parameter, it indicates the agent is frequently operating outside its authorized scope. A high frequency here requires immediate intervention, retraining, or deactivation.
Okay, now for the warnings. Organizations have to actively avoid these governance anti-patterns when designing and deploying these systems, or the entire trust architecture just collapses.
These are the architectural mistakes that create the most risk. The first is reasoning execution entanglement.
Which means the thinking and acting parts are merged.
It's like giving the planning committee immediate, unfiltered access to the vault keys. Allowing the reasoning engine in Layer 2 to execute actions directly without the policy enforcement engine in Layer 5 intervening is a single point of catastrophic failure. If the model is compromised by a prompt injection, it can instantly commit catastrophic actions right to a core database, delete mission-critical records without any mandatory policy check.
The second is a networking security failure, flat network topology.
Deploying agents on a non-segmented network allows for lateral movement and out-of-band communication. This completely undermines the zero bypass policy. If agents can communicate directly or access external services without passing through their mandatory interceptors, the audit trail is compromised and policy enforcement is bypassed. Strict microsegmentation is the non-negotiable architectural solution here.
Third is relying on narratives generated after the fact. Post hoc only explanation generation.
This is a huge risk to integrity. If you only generate the explanation after the action is complete, the agent may simply hallucinate a coherent, plausible justification for its behavior that does not reflect the actual internal reasoning process. Trust requires intrinsic explainability reasoning traces generated concurrently with the plans to ensure the narrative is a truthful representation of the cognitive process, not just a fabricated justification.
And the final, critical anti-pattern. Persistent, broad-scope identity.
As we discussed, granting agents long-lived, high-privileged service accounts creates an unmanageable security footprint. It becomes impossible during an audit to distinguish between different reasoning sessions or different specific agents acting under that shared credential. If you can't tell which digital entity made the decision, you lose all Holmes accountability. The architectural fix is mandatory, identity-aware delegation using task-scoped ephemeral tokens.
So what does this all mean? The sources provide a clear implementation roadmap, advising enterprises on how to scale autonomy gradually through 3 defined tiers. This is a great summary of the organizational responsibility required for deployment.
This roadmap is the path from controlled intelligence to truly dynamic intelligence. Tier 1 is the foundation, or controlled intelligence. The focus is purely on infrastructure. The key architectural patterns are mandatory interceptors, secure tool orchestration gateways, and agent identity management. The outcome must be simple. Every agent action, regardless of complexity, is logged, attributed, and justified.
Then we advance to Tier 2, workflow or structured autonomy.
This tier involves multi-agent interactions, but still within deterministic, well-defined paths. Key milestones here include defining those constrained autonomy zones for specific business units and deploying real-time policy enforcement engines to regulate all interactions. The outcome is that complex processes are transparently decomposed into auditable subtasks with automated quality assessments built right into the flow.
Finally, Tier 3, autonomous or dynamic intelligence. This is the fully realized digital workforce.
This is where agents begin to determine their own strategies based on high-level abstract objectives. This requires significant architectural maturity. Goal-directed planning must be possible, but it must be governed by a global, immutable provenance ledger with distributed consensus. Key safeguards include implementing adaptive learning with active bias monitoring and sophisticated guardrails. The ultimate outcome is a digital workforce that is self-improving, fully auditable, and resilient.
And this demands that every organizational role is involved. The enterprise AI architects designing the multi-tier fabric, the platform engineers enforcing the zero-bypass network segmentation, the GRC leaders defining the declarative policy sets and ethical guardrails, and the AI auditors conducting continuous reviews using metrics like the explanation completeness score. This entire architecture is a collaborative trust effort.
It is entirely cross-functional. The production readiness checklist should be a mirror of this architecture. You shouldn't deploy an agent until you can verify identity with task scope tokens, verify provenance through hash chains and mandatory interceptors, and verify policy compliance with runtime testing of the PEE. If any of those are missing, you're deploying an unmanageable liability.
That brings us to the end of our deep dive into architecting trust. The core idea we've established is that trust in these autonomous enterprise systems is not a one-time certification. It's a continuous, real-time necessity built into the very bones of the infrastructure, relying on mandatory interception, hash chain ledgers, and constant policy enforcement.
We've established that the move to agentic AI is fundamentally a journey of responsibility. Power and efficiency are fantastic benefits, but they have to be secondary to verifiable accountability. The entire structure, from the data authentication at the perception layer to the policy enforcement engine, is designed so that autonomous intelligence and human oversight can coexist in a resilient, secure-by-design ecosystem. Every decision is traceable, every rationale is understandable, and every action is verifiable.
The source material mentions adaptive learning guardrails that monitor drift in decision-making to prevent active bias amplification as the agent learns new patterns. We've talked extensively about the technical controls for the policies defined today, but as these systems learn and change over time, the constraints need to change with them. This raises a fascinating and, I think, very challenging question for future architects.
Considering all the technical controls we've discussed, the PE, the immutable ledgers, the cognitive traces, what level of complexity will the policy enforcement engine need to reach to continuously verify the evolution of an autonomous agent as it optimizes itself and changes its internal strategy? What technical mechanism will prevent an agent from autonomously optimizing itself right out of its ethical or operational constraints over months or years of learning? That continuous governance challenge is the ultimate frontier for trust architecture.